Hello. In today's lesson, we will discuss sound waves. What is sound and how is sound produced? Well, of course, sound is a form of energy and sound is produced by vibrating objects. I have a tuning fork here. I can set this into vibration by simply hitting it. Alright, watch this. When I hit it, beautiful musical note, is that right? Yes. Now, the prongs of the tuning fork are set into vibration. It is vibrating back and forth between a left extreme and a right extreme, and what happens is air gets pushed back and forth. It sets the air molecules into vibration, and that vibration reaches your eardrum, making you listen to the sound or hear the sound. I have a stretched string here. I'm going to pluck it. Hear the sound. Alright, that's the sound. Okay, now sound is produced by vibrating objects. Sound is a form of energy, and the sound energy actually needs a material medium to propagate through. Now, I can make all the sound I please hear, but if there is no material medium between me and the camera, you will not be able to hear me. So sound can only travel through a medium. Sound can travel through air. Sound can travel through water, isn't it? Can sound travel through steel? Yes, it can. In fact, sound travels much faster through steel than it does through air. Where sound is propagated through solids, liquids, and gases in the form of longitudinal waves. Tell me, how does a longitudinal wave differ from a transverse wave? In a longitudinal wave, the particles vibrate back and forth. The energy of propagation is in the same direction. Well, so when a tuning fork vibrates, the prong of the tuning forks vibrates back and forth, and the vibration of the air particles will also be back and forth in the same way. So sound is a form of longitudinal wave. In a longitudinal wave, the direction of particle vibration is the same as the direction of propagation of the particle. Alright? Sound is produced by, of course, vibrating objects. Now here I have shown a diagram of how that looks. I have taken a part of the tuning fork and made it look big. And this is how it's going to vibrate. It vibrates to the left extreme, back to the equilibrium, to the right extreme, and it continues. And look at the way the particles of the medium behaves. When the tuning fork moves to the right, it will push the air particles to the right, creating a region of high density. Particles get pushed to that region. Now, region of high density will move along that medium. Now, when the tuning fork prong moves back, you see, it creates a space, and the air molecules, there aren't very many molecules there, so that is a region of low density. So what happens is, as the tuning fork moves back and forth, as it moves to the right, a region of high density is produced, and the region of high density is propagated through air. And as the tuning fork prong moves back, it creates a region of low density, and the low density also gets propagated. Now, in place of the crest and trough for a transverse wave, what we have in the longitudinal waves are regions of high density and regions of low density. That's what I have drawn here. A region of high density is called a compression. It is written in a very small letter. I don't know whether you can read it. A region of high density is called compression, and a region of low density is called a rarefaction. What does rare mean? Rare is too few. So the compressions and rarefactions advances through the medium. When the compressions and rarefactions reach your eardrum is set into vibration exactly the same way the tuning fork is vibrating, and you hear that sound of the same frequency. Okay, so a vibrating object has an equilibrium position and two extreme positions. As the vibrating object moves from the extreme left to the extreme right, the particles of the medium are pushed to the right, creating a high density region called compression. So compression is created when the vibrating objects move to the right. It creates a region of compression which moves along. When the vibrating objects move back, a region of rarefaction is created, which also is propagated. Now, so a longitudinal wave actually consists of regions of high density and regions of low density called compressions and rarefactions. Okay. The particles of the medium are thus set into simple harmonic motion. I would like you to watch one thing here. Tell me, if a particle is at the center of a compression, what is the direction of motion of that particle? Will that particle be moving in the direction of the wave, or will it be moving away from the wave? Now remember, a compression is created when the vibrating object moves in the direction of the wave. Therefore, a particle at the center of a compression will be moving in the direction of the wave, will be vibrating in the direction of the wave. And a particle at the center of a rarefaction will be moving in the opposite direction. In the same way, if you remember the state of particle vibration for a transverse wave, a particle on a crest has reached its maximum displacement, it is now beginning to move down. Particle on a trough is beginning to move up. You see that? They are completely in opposite states of vibration. In the same way, for a longitudinal wave, a particle at the center of a compression is moving to the right in the direction of the wave, and a particle at the center of a rarefaction is moving in the opposite direction. When the particles vibrate in the direction of the wave, they are in a region of compression. And when the particles vibrate in a direction opposite to the wave, they are in a region of rarefaction. Well, that needs to be understood very well. Let's move on. The compression and rarefaction in a longitudinal wave are analogous to the crest and trough of a transverse wave. And you know, it is much easier to draw the crest and trough rather than drawing the compressions and rarefactions. So even when we want to represent a longitudinal wave, we will draw them as compressions and rarefactions. But when I draw a compression, remember that is going to represent, I beg your pardon, when I draw a crest, that will represent a compression. When I draw a trough, that will represent a rarefaction. So we will do that as we move on. You can see here I have done that. You can see I have drawn a transverse wave structure here, which the crest represents the compression and the trough represents the rarefaction. Okay? So from now on, if I draw a transverse wave picture to represent a longitudinal wave, you must understand the crest represents a compression and the trough represents a rarefaction. The vibrations of particles at the center of a compression differ in phase by pi. They are completely out of phase. So, the wavelength of a longitudinal wave. Can anybody tell me what is the wavelength of a longitudinal wave? Now remember, a wavelength for a transverse wave is a distance from a crest to a crest. That means for a longitudinal wave, it must be the distance between two nearest compression or the distance between two nearest rarefaction. So the wavelength lambda is the distance between two nearest compressions. Alright, let's have a look at an animation of a longitudinal wave. Now you have seen this before. You can see here the vibration, the back and forth vibration of this red rod set the particles of the medium into back and forth vibration. Now this is, at one look, it is very confusing because it looks like all the particles are moving all the way to the right, but actually not. Look at it. I'm pointing on one particle. Now watch what that particle is doing. It's simply moving back and forth. That particle is executing simple harmonic motion. Every particle in the medium is executing simple harmonic motion. But in some regions, particles are crowded. You can see compression, and you see that compression just moves on. And in some regions, the particles are farther apart, rarefactions. Compressions and rarefactions are created, which then gets propagated. And if you're standing here, your eardrum will vibrate with the same frequency. And if you notice, watch this particle. When this particle is moving to the right, it is in a region of compression. When it is moving to the left, it is in a region of rarefaction. Okay, I'm going to close this one. Let's move on. Let's now talk about the speed of sound waves. Now, which medium will sound travel faster, in air or in water? Have you ever tried listening to somebody in water? If you go under the pool and clap your hand, well, you must be careful doing that because it can break the eardrum of your partner. Because sound travels so fast in sound, it takes very little time to travel that small distance. The speed of sound waves in a medium depends on how fast particle vibrations are transmitted to that medium. It depends on the elastic properties. If particles are bound together much better, like in steel, sound will travel much faster to that medium. You see, through steel, sound can travel very many times the speed in air. It largely depends on the elastic properties of the medium. Speed of sound waves through water depends on the bulk modulus of water. If you remember the first part of the physics, we talked about bulk modulus, is that right? The elastic modulus. So, the speed of sound in water depends on the bulk modulus of water, while the speed of sound in steel depends on the Young's modulus. Can you recall those terms we talked about? Okay, I'm going to give you now a formula for calculating speed of sound in air. The speed of sound in air depends on the air pressure, P, or the atmospheric pressure, because the pressure determines how closely the molecules are linked together. Is that right? Greater the pressure, greater will be the influence of each molecule transmitting to the other. All right. It also depends on the density. And I have the equation here. Look at the equation. V, the speed of sound in air, equal to square root of gamma p over rho. Rho is the density. We generally use the Greek letter rho for density. So V equal to square root of gamma p over rho, where gamma, again a Greek letter, this gamma has a value 1.4 for air. You don't need to worry about that. It has a value 1.4. P is the atmospheric pressure and rho is the density. Now what happens is the value of P divided by rho depends on temperature. That means because the value of P over rho depends on temperature, the speed of sound in air depends on temperature. Tell me, does sound travel faster at low temperature or at high temperature? Well, at high temperature, molecules are more energetic. That means they can transmit sound at a much faster rate. So the speed of sound will be higher at higher temperature. As the temperature cools down, the speed of sound will decrease. And I'm going to give you an approximate relation between speed of sound in air and the temperature. Now, the relation is going to connect V0. V0 stands for speed of sound at 0 degrees Celsius. And Vt stands for speed of sound at 0 degrees Celsius. I'm sorry. V0 is the speed of sound at 0 degrees Celsius. And Vt is the speed of sound at T degrees Celsius. And look at the equation. Vt equal to V0 plus 0.6T. That means for every degree rise in temperature, the speed of sound will increase by 0.6 meter per second. So, the velocity of sound, speed of sound at any temperature T equal to speed of sound at 0 degrees plus 0.6 T. I want you to remember that equation. It'll be useful for us to solve simple problems. Okay, let's do a simple problem. Example 1. Find the speed of sound in air at STP. What is STP? Standard temperature and pressure. What is the standard temperature and pressure? Well, standard temperature is 0 degrees Celsius. That is 273 Kelvin. Alright? And standard pressure is 1 atmosphere. Now, in Physics 1 we talked about 1 atmosphere expressed in Pascal. Now, does anybody recall how many pascals is 1 atmospheric pressure? Well, it's useful to remember that. The normal atmospheric pressure, 1 atmosphere, is 1.013 times 10 to the power of 5 Pascal. And that is the standard pressure, the normal atmospheric pressure. The density of air at 0 degrees Celsius, again, a good result for you to remember. What is the density of air at 0 degrees Celsius? Is 1.29 kilogram per meter cube. So, we know the value of P, we know the value of rho, and you know gamma is 1.4. Therefore, we can now calculate the speed of sound at 0 degrees Celsius, V0. Why? Standard temperature. All these values are for standard temperature, that is 0 degrees Celsius. Therefore, we calculate speed of sound at 0 degrees Celsius is square root gamma P by rho. Gamma is 1.4, P is 1.03 times 10 to the 5 Pascal, and rho, the density, is 1.29 times 10 to the 1.29 kilogram per meter cube. What does that give you? That is 332 meter per second. That's the speed of sound in air at 0 degrees Celsius. Okay, if you now have this, can you calculate the speed of sound at 20 degrees Celsius? Well, I give you the equation. Vt equal to V0 plus 0.6 t. Let's do a problem like that. Determine the speed of sound in air at 30 degrees Celsius. Well, we know the speed of sound at 0 degrees Celsius. We just calculate it. Vt equal to V0 plus 0.6 t. Now we calculated V0 as 332 meters per second. And T is 30 degrees Celsius, so that will be 332 plus 0.6 times 30, and that's equal to 350 meters per second. Now very often we will be required to use the speed of sound at room temperature. What is the normal room temperature? Well, the normal room temperature will be about 20 degrees Celsius. Can you calculate the speed of sound at 20 degrees Celsius using that formula? Alright, calculate that and keep that with you. Whenever I want to use the speed of sound at room temperature, I'm going to use 340 meters per second. Alright, remember that. If I don't give it to you, you use the speed of sound at room temperature to be 340 meters per second. Let's now talk about intensity and intensity level of sound waves. What does intensity mean? Alright, let's talk about it. A vibrating object sends out energy in all directions. Is that right? Now, if I have this object vibrating here, alright, let's keep it vibrating. It sends out energy in all directions, in 3 dimensions. Energy goes in all directions. Now, intensity is a measure of, now intensity of course varies with distance. You see, if I keep the object here and you stand very far from it, the amount of energy reaching you will be very small. Now, suppose the object is vibrating here. If I draw a circle around here, the amount of energy crossing any point on that circle will be a considerable amount of energy. If I draw a circle outside, the amount of energy crossing any point on that circle will be less. So I move away from the vibrating object, the amount of energy reaching me becomes less and less and less. So intensity of a sound is related to the amount of energy reaching a particular point from the source. Now, how do we define that? The amount of energy emitted by the vibration in 1 second is called the power emitted by the source. So when an object is vibrating, that object has a power. Don't you talk about the power of a loudspeaker? Yes. You say, oh well, my car loudspeaker is 300 watt. I'm sure most of you will say that. Why? What does that mean? Now, 300 watt is a measure of the energy emitted by that source in 1 second. So, this vibrating object has a power, the amount of energy emitted per second. Alright? And what is the unit for measuring the power? Power is measured in watt. So this vibrating object has a power, the amount of energy emitted per second measured in watts. Okay. I have now defined the intensity of a sound at a particular point. See whether you can understand it. Intensity of sound at a point. We define intensity at a point. In other words, this is the source and the point is somewhere here. How do you define the intensity of the sound produced by this force at this point? Look at this. Intensity of the sound at a point distance r from the source is a measure of the power crossing at right angles to unit area containing that point. Well, let me see if I can use the whiteboard and draw something for you. All right. Suppose this is the source here. It's emitting energy in all directions. I want to find the intensity at this point. So what I'm going to do is I'm going to keep an area of 1 meter square, a unit area. You see that? We have the energy crossing at right angles to a unit area containing that point. So what I have done is I have constructed a unit area containing that point. And now, how much energy is crossing that unit area? You can see, if I draw these lines, now I can measure the amount of energy crossing that unit area, and that will be a measure of the intensity at that point. So intensity of sound at this point is a measure of the amount of energy crossing unit area containing that point, and energy crossing at right angles. Now, if I take that point, say somewhere here, all right, let me do that. If I take this point and keep it there, look at that. I'm going to keep my unit area there. Now, the energy that is crossing that area, you notice that all the energy that was crossing this unit area, not all of it will reach this area. That means as you move away, the amount of energy crossing unit area will become less. The intensity becomes less. Alright? So read that one more time and see whether you can understand. What is the definition of intensity of sound at a point? The intensity of sound at a point, distance r from the source, is a measure of the power crossing at right angles to unit area containing that point, placed at that, containing that point. Intensity I, we will represent intensity by the uppercase I, is measured in watt per meter square. You see? Power crossing unit area, watt per meter square. Intensity is measured in watt per meter square. Take a note of that. Now, what is intensity level? Don't confuse between intensity and intensity level. Intensity level of the sound determines its loudness, how loud the sound is. Now, higher the intensity, louder will be the sound. They are not the same thing. It is the intensity that determines the intensity level. All right. The intensity level is actually represented by the Greek letter beta. It is a logarithmic function of the intensity, and it is given by this equation. Beta equal to, what does beta represent? Beta represents the loudness, the intensity level. Intensity level equal to 10 log I over I0, where I is the intensity of the sound at that point, and I0 is called the threshold intensity. What is the threshold intensity? Threshold intensity is the intensity of a sound that you can barely hear. In other words, there is no sound below that you can hear. Now, for example, can you hear that sound? I can, very barely. That is the threshold of intensity. Maybe you can slightly now. I have gone above the threshold of intensity. So I0 is the minimum intensity of a sound that is audible to our ears. And I is the intensity of the sound reaching that point. So the intensity level, and what is the unit in which intensity level is measured? We measure it in a unit called decibels. So the intensity level measured in decibels equal to 10 log I over I0, where I is the intensity of the sound and I0 is the threshold intensity, and this is the value of I0. So whenever you want the value of I0, you must use this. I0 is 10 to the power of negative 12 watt per meter square. Okay, the intensity level beta is measured in a unit called decibel. Look at where you write decibel, small d and big B. Decibel is the unit used for measuring intensity level. And what is the unit used for measuring intensity? It is watt per meter square. So don't confuse between these two. Notice that the difference between intensity I measured in watt per meter squared and the intensity level beta measured in decibels. Okay, here I have given you a table, some approximate decibel values of some common sounds. Look at this. Rustling of leaves is about 10 decibels. Normal breathing. Can you hear the sound of normal breathing? That is the threshold. What is the intensity of the threshold? Is 10 to the power of negative 12 watt per meter square. Alright, busy traffic is about 70 decibels. Alright, construction noise is about 100 decibels. Rock concert is about 110 decibels. Alright, when will pain begin to come in your ear? Well, you have a rock concert is very close to the pain, to the pain threshold. In fact, most young people these days plug their ears with earphones and jack up the music. Is that right? Now, you don't understand that most of the time the decibel level is very high. You are actually harming your eardrums. Now, I have read the statistics that among 30 to 40-year-olds, visits to the doctors with problems with hearing is in the increase. The reason is all those music. So young people, be careful about taking care of your hearing. Let's do a small problem. What is the intensity level of a sound of intensity I equal to 10 to the power of negative 10 watt per meter square? We need to find the decibel value, the intensity level of this intensity sound. Well, what all we need to do is go back to a formula. What's the formula? Beta equal to 10 log I over I0. I is given to you 10 to the power of negative 10. What is I0? I0 is 10 to the power of negative 12. So that will be 10 log 10 to the negative 10 over 10 to the negative 12. Anybody tell me quickly, you've all done your pre-calculus. 10 to the negative 10 divided by 10 to the negative 12 is, anybody? Yes, it is 10 to the power of 2, because this one goes to the numerator will become plus 12, and plus 12 minus 10 is plus 2. So that will be 10 log 10 to the power of 2. Okay, how many of you can tell me what is log of 10 to the power of 2? Log of 10 to the power of 2 is 2. You see? Now, log of x to the power of a to the base x is a. And in our case, the base is 10. So, log of 10 to the power of 5 is 5. Log of 10 to the power of negative 2 is negative 2, and so on. You must know this. Okay. So, log of 10 to the power of 2 is 2. 10 times 2 is 20. So, a sound of intensity 10 to the power of negative 10 watt per meter squared has an intensity level of 20 decibels. Let's do another one. The sound of a dog's bark is 50 decibels. So at this time, I gave you the decibel value. What is the intensity of the bark? You got to calculate the I value. The intensity of a rock concert is 10,000 times that of the dog's bark. What is the intensity level of the rock concert? Alright, let's first do the first part. You are given the decibel value, beta equal to 50 decibels. And you know I0 is 10 to the power of negative 12 watt per meter squared, right? Alright, and we need to find the value of I. So beta equal to 10 log I over I0. We know the value of beta, you know the value of I0, we need to find the value of I. For that you must recall your logarithm. Let me ask you this. Now, if 5 equal to log of 2, no, log of x, let's say. If 5 equal to log of x, then can you solve this for x? What is x equal to? You see, log of x means log of x to the base 10. Now, this statement means x can be obtained by raising this base 10 to this power 5, or x equal to 10 to the power 5. Alright, one more example. Suppose I have 2.5 equal to log of y. Now here log of y means the base is 10. So what is then y equal to? Y equal to, the base is 10, 10 raised to the power of 2.5. You must know this logarithmic equation solving process. Okay, let's move on. Okay, that is 50 equal to 10 log I over 10 to the power of negative 12. And now, well, there's an easy way probably. I can now write, how many of you know log of I over 10 to the negative 12 can be written as log I minus log of 10 to the negative 12. You know that? Well, tell me, what is log of 10 to the negative 12? Log of 10 to the negative 12 is negative 12. So that will be 10 times log I minus negative 12 is plus 12. Alright? And that is 10 log I, distribute that 10. 10 log I plus 10 times 12 is 120. And the left hand side is 50. And if I now take this 120 to the left, I get 50 minus 120. 50 minus 120 is negative 70. That negative 70 equal to 10 log I. And therefore, what is log I equal to? Divide both sides by 10. Log I equal to negative 7. Now, if log I equal to -7, what is I equal to? I just showed you how you can solve this. If log I equal to -7, then I equal to 10 raised to the power of -7. That's right. I equal to 10 raised to the power of -7. All right? You must practice these kind of problems. It's very important. Okay, let's do the second part. The intensity of a rock concert is 10,000 times that of the dog spark. This is the intensity of the dog spark. And therefore, what is the intensity of the rock concert? 10,000 times this. So the intensity of the rock concert is 10,000 times 10 to the -7 watt per meter square. What is this equal to? What is 10,000 times 10 to the -7? You must be able to tell me. That is 10 to the -3. You see, 10,000 is 10 to the +4. 10 to the +4 times 10 to the -7 is 10 to the -3. Well, we now know the intensity of the dog spark. Can you calculate the intensity level? Well, we now know I, we know I0, therefore we can calculate beta. So beta equal to 10 log I over I0. I used I equal to 10 to the -3, I0 equal to 10 to the -12. Alright, now tell me, what is 10 to the -3 divided by 10 to the -12? Can you get that quickly? Well, this 10 to the -12, when it goes to the numerator, becomes 10 to the +12. And 10 to the -3 times 10 to the +12 will be 10 to the +9. So that will be 10 log 10 to the power of 9. And what is log 10 to the power of 9? Log 10 to the power of 9 is 9. And so the decibel value is 90 decibel. The intensity level of the dog's barking is 90 decibels. This is a good problem, and you can do actually many problems once you know how to do this one. Okay, I'm going to go on to the next concept, that is pitch of a sound. What is the meaning of pitch of a sound? When you hear a sound, now this sound has a pitch. Alright, you heard the pitch. Now how about this sound? Do they sound the same? Listen to this again. The first sound. Alright. Now, which of these is high? You see, pitch is the sensation when you hear a sound of high sound or low sound. Now, how about the pitch of that sound? What is pitch of a sound? The quality of a sound wave which determines how low or how high the sound is called the pitch of the sound. When an opera singer sings, you can see the pitch goes from very high, ah, like that, is that it? To ah, low frequency. A man's voice generally is bass, ah. A woman's voice, ah, high. High pitch, low pitch. Is that right? All right. Well, I'm not joking anybody. I'm just trying to make a point here. All right? All right. Pitch is primarily determined by the frequency. So, when an opera singer produces a very high-pitched voice, her voice cord is vibrating at a very high frequency. And when a man's voice is very flat, oh, well, the voice cord is vibrating at a low frequency. So pitch is primarily determined by frequency. of vibration. But pitch is not really the same. You cannot say pitch is the same as frequency, because frequency is the physical characteristic of sound. In other words, it tells you how many times this vibrates a second. Whereas pitch is the listening sensation you get. You see that? The difference? If two people hear something, it may sound slightly different. For one person, it may be slightly different pitch. But I will try and explain that a little later. While frequency is the physical quantity that determines the pitch, the sensation a listener gets is what defines the pitch. Alright, pitch is what the listener hears. Now, a very important and interesting phenomenon in sound is what we call the Doppler effect. Now, anybody heard about Doppler effect? Have you ever stood in a place when a car is coming towards you, blowing its horn? How does it sound? Now, if I try to imitate it, I know you will laugh at me, but if a car is coming towards me blowing its horn, it would sound "ah!" In other words, the frequency all of a sudden seems to be rising sharply. And how will it sound if the car just moves away? "Ah!" Have you ever experienced that? Now, does it mean that the frequency of the horn is changing? But the frequency of the horn is not changing. But what you hear is changing. As the car comes closer and closer towards you, you hear louder and louder pitch. As the car goes away from you, you hear a low pitch. Now, try and listen to this and see whether you can hear this. I'm trying to imitate that here. Now, here is the car coming towards you. Can you hear that? I don't know. Try once again. The frequency is increasing. Now, I'm now trying to send the car away from you. Did you hear that? Now, I'm going to try both. Car coming towards you. Car going away. Once again. Alright? So you hear the different sensation of pitch as the car comes towards you and goes away from you. Well, this is actually Doppler effect. If a source of sound moves towards the listener, the pitch of the sound heard by the listener is different from the pitch if the source was stationary. This means that the apparent frequency of the sound reaching the listener is different from the actual frequency of the source. Now, I want you to watch these words I'm using. The apparent frequency. The frequency as you hear is not really the actual frequency of the sound. That frequency you hear is slightly different. That's why I call it the apparent frequency. So the apparent frequency of the sound reaching the listener is different from the actual frequency of the sound. When there is relative motion between the source and the listener. And this apparent change in frequency of a sound due to relative motion between the source and the listener is called Doppler effect. So if I ask you to give me a sentence on Doppler effect, I want you to write down now. Or write a paragraph on Doppler effect. Can you? Alright. Now look at this picture here. Now, I have something that is generating waves in water, and I've moved that source to the right. Now look at the difference here. When the source is moving to the right, the waves on the right, that is, the waves where the object is moving to, gets compressed. And look at the left side. The waves get elongated. Why? Because the source is moving towards you. The waves that are produced get compressed in that region. And on the other side, the waves get elongated. That means if you stand here, more number of waves will reach you per second. Now, tell me, what is your understanding of frequency of a sound? Suppose I say the frequency of this sound is 400 hertz. What do you understand by it? Well, you must understand it in many different ways. This object vibrates 400 times a second. Also, it generates 400 waves per second, because for each complete vibration, it generates one wave. So it generates 400 waves per second. Also, you are hearing it. That means 400 waves are reaching your eardrum per second. Now, when you listen to the sound from here, actually more waves will reach you than the number of waves generated. And that's why the apparent frequency becomes higher. Alright? Okay, so the wave source moving to the right. Look at the separation between the waves in front of the source and behind it. What difference do you notice? We just talked about it. Now, what does the separation between the two waves actually represent? The separation between here, this is a wavelength. You see that? That means the wavelength of the waves to the right of the source is smaller than the wavelength of the waves to the left of the wave. The waves get compressed in the direction of motion and get elongated in the other direction. So, the separation between two waves is a measure of the wavelength. Let's go and talk more about it. Now, we now talk about a source moving towards a stationary listener. Here we have a source moving towards a stationary listener. An ambulance moving towards a stationary listener. That means, you see, the waves in front of it are all compressed and the waves on the other side are stretched apart. If the source is stationary, the waves will look like this. Everywhere the wavelength is the same. But now, when the ambulance is moving to the right, the wavelength to the right is shorter than the wavelength to the left. That means the listener will now get more number of waves reaching. That means the apparent frequency will now be greater. Let the velocity of the sound be v and the velocity of the source be vs. Now, if the source is not moving, the waves produced by this source will spread out in a circle of radius v. What does the speed is v means? The speed is v means the wave will move a distance of v meter in 1 second. So, all the waves produced in here, if the source is not moving, will move a distance v. Now, since at that time the source has moved a distance, now during that time all that waves is now compressed to that region v minus vs. You see that? Originally, when the source was not moving, these waves were in a region v. And because the source is now moving to the right, all those waves are now compressed in a region v minus vs, where vs is the speed of the source. There you are. Therefore, if f0 is the actual frequency of the source, there will be f0 waves produced in 1 second. There will be f0 waves in that region. And all those f0 waves are now compressed in that small region of v minus v0. So what is the wavelength of each wave here? Now remember, wavelength is V over lambda. Is that right? Let's do that. If lambda prime is the wavelength reaching the listener, then lambda prime will be V minus Vs divided by F0. In other words, this is the region where these many waves are compressed. So the length of the region divided by the number of waves will give you the apparent wavelength. And that is the wavelength that is reaching you. And look at the way I'm going to write it. I'm going to factor out a V. Now how do I factor out a V? What I do is I multiply there. Alright. What I did is I multiplied this by V and divide by V. Look at this. I multiplied by V and divide by V. I factored out the V, leaving a 1 minus Vs over V there. Alright? So that will be, okay, so that will be V times 1 minus Vs over V divided by F0. Now, if F prime is the frequency as the listener hears, then F prime will be equal to what? V over lambda prime. And that lambda prime is this. Let's do that. So that will be V over V times 1 minus Vs over V over F0. And that will be F0 over, take V as the common denominator. That will be V as the common denominator will be V minus Vs. And what is that equal to? Now, I would like you to remember this equation. You can forget everything I said now, but the frequency as you hear when a source is moving towards you will be V over V minus Vs. V is the speed of sound, Vs is the speed of the source, F0 is the actual frequency of the source. Alright, now what happens when a source is moving away from you? When a source is moving away from you, here you have the situation. You are standing here and the source is moving away from you. This time the waves are stretched out in a region V plus Vs. That's the only difference. And I will get F prime equal to F0 over 1 plus Vs over V. And that simplifies to V over V plus Vs. The only difference is previously we had V minus Vs. This time we have V plus Vs. So this is the frequency as you hear when a source is moving away from you. And that will be a lower frequency. Now, if the listener is moving towards the source, I will write the equation. You don't need to worry about this. I'm going to give you one more, listener moving away. Now, mostly we will be using this equation and the equation for the listener stationary and the source moving towards you. Well, since the tape is going to finish, let's see if we can get to one problem. A source of sound that emits a sound of frequency 200 Hz, F0 is 200 Hz, moves towards a stationary listener with a speed of 80 meters per second. Well, Vs is 80 meters per second. If the speed of sound in still air is 340 meters, find the wavelength of the wave between the source and the listener. Well, we got the frequency of the source is 200 Hz, speed of the source is 80 meters per second, and speed of sound is 340 meters per second. Is that right? That means all those waves produced, how many waves are produced? These 200 waves are now spread out in this region, V minus Vs, which is 340 minus 80 in 260 meters. So these 200 waves are spread out in this 260 meters. What is the wavelength? Will be V minus Vs divided by F0. That will be 1.3 meter. what is the frequency heard by the listener? The frequency heard by the listener will be V over lambda prime, which is 340 over 1.3. That is 261.5 Hertz. Now what I would like you to do is go back and look at the PowerPoint presentations I gave you. I have worked out a few more problems for you. I would like you to look through those problems and get familiarized in doing these kind of problems. I'm going to stop this here because my camera tape is finishing. And I will get back to you for the last lesson of this unit. Alright? I will get back to you very shortly. Alright? I'll see you then later.